So coming back to the discussion, now if you have a linear molecule, okay, there is it's stretching molecule, then what will be the number of the vibrational degree of freedom, or what can be the number of peaks? Okay, so here when you say there is a formula for this 3n minus 5, where n is the number of atoms. Now here, if you take the carbon dioxide molecule, it is 3 into 3. 3 atoms are there, carbon 1 and 2 oxygen. So therefore there are 3 number of atoms, not type. Type is 2, but there are number of atoms is 3. So 3 into 3 is 9. 9 minus 5 is 4. Now if you see this one, 4. 4 degree of freedom will be there. So what are these? 2 are stretching modes and 2 are bending modes. Now one stretching mode is symmetric stretching mode, another stretching mode is asymmetric stretching mode, and bending, it is both are scissoring, okay, and both are just the same, one moving out of it. So both the scissoring vibrations are almost equivalent. Now let us go to the next one. Next one, if it is a non-linear molecule, means it is having having angle between the bonds. So what will be the formula? What is the number of vibrational degree of freedom? So we will be having thrice n minus 6. If we take an example like water, oxygen, H, it is a non-linear molecule. So it is 3 into 3 is 9. 9 minus 6 is 3. How do we take account of it? And we take account of it. One is symmetrical stretching, both the bonds are coming lengthening similarly, and asymmetric, one is lengthening, one is shortening, and another is scissoring. Scissoring means it is going in, both are going in and both are going out. This is scissoring. Achha. Now see, these are the fundamental mode or normal mode of vibration, and they occur without change of center of gravity of the molecule. Okay, this other bending vibrations will be there, but it will be what? It will be having a change in the gravity, center of gravity of the molecule. What are non-fundamental vibrations? Overtone, combination tones, and Fermi resonance. Now what is this? You can see it here in elaborate way. IR spectrum shows bands rather than line spectra due to the coupling of various rotational transition. Within rotational means you are going to the next energy, that is microwave. Now when you are giving more energy, automatically the lesser energy also comes into it. Okay, so whenever there is a vibrational transition, there is automatically rotational transition also. Rotational transition is coming in the range of microwave frequency. Okay, so vibrational transition happening, and accordingly rotational transition is also happening. IR spectrum is generally complex and contains many bands in addition to ones corresponding to the fundamental vibrations. Those which are due to the fundamental vibration, we have already discussed it. It is non-fundamental vibrations. Say for example, overtones. What are overtones? Bands corresponding to the integral multiple of the fundamental vibration. Say for example, they are due to transition from ground state to the higher vibrational state. Now once it happens, they are very weak bands. Okay, so as soon as it happens, say for example, an absorption band at 1500 centimeter inverse may well have an accompanying band of 2100 and 3150. Means if this is new, this is twice new, this is thrice new. So these are overtones. Okay, these are overtones, means due to the first vibration, the other vibrations has also come into, other peaks has also come into existence. Okay, now combination bands, two vibrational frequencies in a molecule coupled to give a new frequency within a molecule. So combination bands, So coming two vibrational frequencies in a molecule coupled to give, if they are nearby, definitely, okay, so they will couple to give a new frequency within the molecule. This band is a sum of two interacting bands. Difference band similar to combination band. The observed frequency is the difference between the two interacting frequency, means there can be both addition and as well as there can be a subtraction. So this is difference band. Fermi resonance, when a fundamental vibration coupled with overtone or combination band, the coupled vibration is called Fermi resonance. Now, this vibrational frequency is based on Hooke's law. What this Hooke's law tells us, this frequency depends on two factors. One is the strength of the bond, another is the mass of the atoms. Okay, or you can say the reduced mass of the atom. Now, here the Hooke's law is 1 by twice pi c. All these are constants, and k is the force constant. Stronger the bond, the greater will be the frequency. And what is mu? Mu is the reduced mass, means heavier the atoms, lesser will be the frequency. Heavier the atoms, lesser will be the frequency. Next is, what is reduced mass? 1 by mu is equal to 1 by m1. Okay, so this is what is so what is mu? Mu is equal to m1 m2 by m1 plus m2, means just work it out. 1 by mu is equal to 1 by m1 plus 1 by m2. From the above equation, it is apparent that stronger the bond, higher the vibrational frequency, higher the mass of the atoms, lower the vibrational frequency. Take this as an example. This is stronger bond, it is having higher frequency. Double bond, little lesser. Single bond, even lesser. Now, if you add one more hydrogen to it, what you see? Now it becomes heavier atom, more heavier. And this is what this if it is the reduced mass. So if it is the mass is increasing, so frequency is also increasing. Means it is inverse. So here we are going for only CH bond. CH bond. Now in this CH bond, you can see this is this carbon is sp hybridized. So this bond, this single bond, is having 50% S contribution. Okay, and accordingly it is having more S percentage. So this bond is stronger, whereas you have here 33% S percentage and it is 25%. So this bond is weaker, bond strength is less, bond strength is in between, and bond strength is highest. So since the bond strength is highest, the frequency of vibration is more, then this is less and this is much lesser. Now go to this one. This is, we have C carbon bonded to different atoms. If it is CH, you know this is H is much lighter. Okay, the mass is very less. So accordingly, mass less and hence frequency is more. Carbon mass little more than H, so frequency is little lesser. Mass is more, frequency is lesser. It is more, even it is heavier than carbon, so it is even lesser. It is heavier than oxygen, it is even lesser, and accordingly Br and accordingly I. Okay, if the mass increases, the frequency of vibration decreases. Also, we have to know that if it is stretching, it will be having more frequency. If it is bending, it is having lesser frequency. Force constant for bending is smaller than stretching. So, in case of this one, this in case in bending, the bond strength is not actually changing, only the angle is changing. So, therefore, its contribution is even lesser and frequency is much less. Now there are certain selection rules, okay, for vibrational transition to happen. For a particular vibration to be infrared active, there must be a change in dipole moment. Those vibrations which are happening but which are not changing the dipole moment of the molecule, those will be infrared inactive. In other words, transition dipole moment must not be zero. Homonuclear diatomic molecules are inactive in infrared because they do not have a dipole moment to start with, and during the vibration also the dipole moment is zero. Say for example H2, O2 and 2, these are all having no dipole moment in the beginning also, and during the vibration also there is no change in dipole moment. In heteromononuclear diatomic molecules such as carbon CO, carbon monoxide, and O are active in iron. Okay. Symmetrical polyatomic molecules like carbon dioxide, is symmetric stretching is infrared inactive, whereas an asymmetric stretching is infrared active. Why? Because of the change in dipole moment when there is an asymmetric stretching. Also, there is an important selection rule. A vibrational transition can happen only from one level to the next higher level. Okay. So, if it is from 0, it can go to +1. If it is from +1, it can go to +2. It cannot go from +1 to +2 or +3. Okay. Transition can take place between adjacent vibrational levels like 0 to 1, 1 to 2, etc. So that's all for today. Thank you so much.